Let's start about magnetic properties of material. In the last class, we saw the hysteresis loop, of ferromagnetic material and ferrimagnetic material. The hysteresis loop is like, if I can share the screen. The hysteresis loop is like that. This is the original magnetization, and if you demagnetize a ferromagnetic particle, it will take the path, this path, not the original path. So magnetization and demagnetization makes the hysteresis loop. This is the curve of magnetic flux density versus magnetic field strength H. Flux density in this side and magnetic field strength is in this side. This R is known as remanence. This R is known as remanence, and this C is known as coercive force. This C is known as coercive force, and this R is known as remanence. Now, again, just a recollection, just for recollection, how it happens, how hysteresis loop occurs. It is because in the ferromagnetic particle, we will see some domains. We'll see some domains where the dipoles are oriented in the same direction. This is one domain, this is another domain, and this is another domain. There are several domains, depends on the what type of material it is. That means what type means as it is either crystalline or polycrystalline. Depending on that, the number of domains are there. So this is one domain, and this is another domain. This is known as domain wall. This is known as domain wall. This is a normal ferromagnetic substance before magnetization. What do you mean by before magnetization? Before magnetization means if you apply the lines of forces of external magnetic field H on this type of ferromagnetic substance, then it is called magnetization. Now, normally in the ferromagnetic substance, this is a small unit of magnet. This is a small unit of magnet. This is a small unit of magnet. But you see here that this small unit of magnet, the dipole is oriented upwards, and in this small unit of magnet, the dipole oriented downwards. So they cancel each other. So like this, in all ferromagnetic, in a ferromagnetic substance, all the domains cancels one another, and hence a ferromagnetic substance is non-magnetic before magnetization. After magnetization, what will happen we'll see later. But before magnetization, you see, although this is a magnet, this is a small magnet, and this is a small magnet, but their magnetic field will cancel each other. For that, this portion is say non-magnetic, and like this is a small magnet, and here there is one whose direction is in the opposite side. So this will not this will cancel each other, and the whole substance, the whole ferromagnetic substance becomes non-magnetic before magnetization. Now, what will happen if we place a ferromagnetic substance uh, under the field of external magnetic field? Under external magnetic field, what will happen if we place this type of substance under external magnetic field? So you'll see the curve. You'll see the curve. If we place this type of substance, if we place this type of substance, say for example, we can write this type of substance by this one in this way, another one is in this way, another one in this way, another one is in this way. This is one small section. This is another small section. This is another small section. Say for example, this is one section. So this is say one section. Now, if we increase the applied magnetic field, we have placed this ferromagnetic substance in presence of an applied magnetic field. Now, if we increase the magnetic field, you'll see these are the domain walls. This is one domain wall, this is one domain wall, this is one domain wall, this is one domain wall. These domain walls moves. This domain wall moves. So if we place a ferromagnetic substance under the external applied magnetic field, the domain wall of ferromagnetic substance moves. You see, if we increase it, the domain wall, this domain wall was here in the middle, it moves to the left. And if we increase the applied magnetic field, you see all the domains are equal, but here all the domains are not equal. Someone is larger and someone is smaller, and the domain wall is moving. And here you see one of the domain wall is lost. One of the domain wall is vanished. See, here there is 4 domain walls and here's 3. And if you increase the applied magnetic field further, there is no domain wall. That means if you place this type of substance under the applied magnetic field, this type of substance means a ferromagnetic substance or a ferrimagnetic material under the applied magnetic field. Uh, mm, 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 uh, uh, After increasing the the applied magnetic field, upon increasing the applied magnetic field, this domain wall moves, and at one time there will be no domain walls, and all these dipoles will be in the same way. All the dipoles will be in the same way. In which way? In the direction of applied magnetic field. So when all the dipoles becomes in the direction of applied magnetic field, say for example, the applied magnetic field is in this direction. When all the dipoles are becomes in the direction of applied magnetic field, then we call it a saturation point. This point where there is no domain wall and all the dipoles are aligned with the applied magnetic field, then we call the saturation point. There is a saturation point which we denote B set. This is magnetic induction B. What is magnetic induction? Magnetic induction means the magnetic field then produced by this applied magnetic field. That is called magnetic induction. That means the secondary magnetic field. So, here they are called saturation point. Now, what will happen if we increase the applied magnetic field more and more? What will happen? Nothing will happen, because all the dipoles aligned with the applied magnetic field. So there will be no change, and the curve will be flat like that. The curve will be flat like that. So after saturation point, the B B, that means the magnetic induction will not increase at all after the saturation point. So if you apply magnetic field more and more and more, if you increase the applied magnetic field more and more, after saturation point, you will not find any increase of magnetic induction. That means magnetic susceptibility of a ferromagnetic substance. So this is the curve for a ferromagnetic substance. This is the curve for a ferromagnetic substance. But if you see the diamagnetic and paramagnetic substance, it will be like that. It is a straight line. It is a straight line for diamagnetic and paramagnetic substances. That means if you apply magnetic field, the magnetization increases linearly. But here it is not linear. It is somewhat curved, and after some time there is some saturation point here. So this is the curve of ferromagnetic and ferromagnetic substances, and this is the curve for diamagnetic and paramagnetic substance. If you apply magnetic field on a diamagnetic or paramagnetic substance, the magnetization or the magnetic flux density B will be like that. And if you apply magnetic field on a ferromagnetic substance, the flux density or magnetization will be like that. This is the curve. This is the curve we saw here. Okay. Now you have applied, say you have applied a magnetic field, and at this point the saturation, you found the saturation. At this point they found the saturation, and say for example this is the value of applied magnetic field where you got the saturation. Now you want to decrease the strength of applied magnetic field. What will happen if you decrease the applied magnetic field? When you have increased the applied magnetic field from 0, it goes like that. And if you decrease it from here to 0, it will not follow the same path. It will not follow the same path. So this saturation is the irreversible process. It is not reversible. That means it will not follow the same path. It will follow, say for example, this is the saturation point. Now you are decreasing the applied magnetic field. You have applied you are decreasing the magnetic field that you have applied. Now, say for example, you have applied 10, uh, mm, mm, 10 something, whatever it may be the unit, you have applied 10 for the saturation. Now you want to decrease it. Say for example, you have applied 9, you have applied 8, you have applied 7 up to 0. Now what will happen? It will not follow this path. It will follow by this way. It will follow by this way. And as the applied magnetic field decreases, the rate of decreasing the applied magnetic field is not equal to the rate of decreasing the magnetization or flux density. That means the secondary magnetic field B. So the rate of decreasing the applied magnetic field H is not equal to the rate of decreasing B, and be always behind H or be always less than H. Be always less than H. When you decrease the applied field, when you decrease the applied field H, so be always less than H. This phenomena is known as hysteresis. This phenomena is known as hysteresis. Now, you have decreased the applied field up to 0, but B is not 0 at that time. B is here. B is not 0 at that time. You decrease the applied magnetic field towards 0, but you will get some magnetic moment to the ferromagnetic material you have placed to the applied magnetic field. So you will get a magnet. So you'll get a magnet here. So how you can get a magnet? If a ferromagnetic substance, if you take a ferromagnetic substance, you apply magnetic field on it, and you decrease the applied magnetic field, then the ferromagnetic substance, becomes a magnet because its magnetization is not 0. You will have this remanence. You will have this remanence extra. That R is this point. R is known as remanence point. Now, if you want to see when B becomes 0, now you want to see when B becomes 0. Now, what you will have to do? You decreased H to the 0. Now, what you will do? You will apply magnetic field in opposite direction. That means H becomes minus S. You apply magnetic field in the opposite direction when H becomes minus S. So when H becomes minus S, you are applying in opposite direction. B is decreasing, and at a time at one negative point, you will find that B becomes 0. This point is known as coercive force or coercivity. This is known as coercive force or coercivity. Now we have explained this portion of the of the curve. We have explained this portion of the curve, and as well as we have explained this portion of the curve. Now, what you want to see? Now, here the applied field is in the negative direction. Negative direction is means you have applied field opposite to that initial field, opposite to the initial field. Now you want to see where is the saturation here. What do you mean by saturation? When when all this when all this in the same way, that is called saturation. So in the positive direction, say for example, in the positive direction, all these arrows, all these dipoles becomes in this direction. And what will happen in the negative direction? All these dipoles becomes in this direction, in the opposite direction. All these dipoles will be in the opposite direction, in this direction, opposite to this, in this direction. So when all these dipoles will be in the opposite direction, that is known as saturation in the opposite direction. This is known as saturation in this direction, and this is known as saturation in the opposite direction. So this point from here to here, you are applying, you are increasing the applied magnetic field in the opposite direction, and here comes the saturation in the opposite direction. That means here saturation in one direction, and here saturation is another direction, is in another direction. Now you are again increasing this towards 0. Then it will become again, it will increase to here. It will again increase to here and up to this again. This is the opposite of this curve. This is the opposite of this curve. This is known as, this is like a loop. This is like a loop, and this is due to hysteresis. So it is known as hysteresis loop. This is known as hysteresis loop. All the magnetization and demagnetization. What do you mean by demagnetization? This is magnetization in one direction. In one direction, this is called magnetization, and here it comes, it is demagnetization, where B becomes 0. This is demagnetization. You magnetized B, and here you demagnetized B. Again, you magnetized B, and here you demagnetized B. Again, you have magnetized B. So this loop is for, this hysteresis loop is for magnetization and demagnetization for a ferromagnetic or a ferromagnetic material. Magnetization and demagnetization for a ferromagnetic and ferromagnetic material. So this is the hysteresis loop, and every magnet, actually every magnet works on this principle. Every magnet works on this principle. Now, this magnetization and demagnetization, this magnetization and demagnetization varies from material to material. There are, say, for example, there are many types of ferromagnetic material or ferrimagnetic material in the world. So this hysteresis loop varies from material to material. In case of some materials, this hysteresis slope is small. In case of some materials, it is big, or it may be flat, or it may be thin. There are many types of hysteresis slope for many types of materials. But for a single material, you can find the saturation point is different. For a single material, say for example, iron is a ferromagnetic material. You will find for a single material, for iron, the saturation point is different. This is called anisotropy. Anisotropy. You'll see anisotropy of material, magnetic material rather. Magnetic material. How it forms? Actually, why for iron you will get the different saturation point? You'll see here. This is iron. This is curve for iron, and this is curve for nickel. You'll see this is the curve for your nickel. You'll this curve is for when you apply external magnetic field in 100 plane. Can you remember what is 100 plane? What is 110 plane? What is 11 plane? That are HKL planes. You read in the solid state chemistry, HKL planes. You will find actually this hysteresis loop depends on the crystalline structure of material. If it is a polycrystalline material, then it will be one type. If it is a single crystal, that will be another type of loop for a single element. Say, for example, for iron, if iron is polycrystalline, you will get one type of loop. And if it is a polycrystalline, then you will get another type of saturation point or another type of loop. And if it is and this hysteresis loop depends on temperature also. If a temperature is high, then your atoms will go haphazardly, will run haphazardly, and it will not be in the same direction. It will not be in the same direction. So I told you that is called Curie point for the ferromagnetic substance. Now, if you magnetize a nickel material, if you magnetize a nickel single crystal to the 100 plane, you will see the saturation comes at C point. You will see the saturation comes at C point. But if you magnetize through the 110 plane, you will get the saturation at B point. And if you magnetize it along 111 plane, you will get the saturation at A point. You see, this A point is much less than B and C. This A point is much less than B and C. So, so this is the anisotropy, direction oriented. Anisotropy means direction oriented. If you magnetize one direction, here you'll see in case of iron, if you magnetize it at 100 plane, you'll get saturation at much less than 110 and 111 plane. So this is the anisotropy of magnetic material. You have to magnetize. You have to magnetize in a particular direction. In which direction you have to find it, but you magnetized in a particular direction for the easy magnetization. For easy magnetization, you will get saturation point here if you get if you magnetize in 111 plane. For easy magnetization, you have to magnetize a ferromagnetic material or a ferromagnetic material in a particular direction. You cannot magnetize it in all direction. You can magnetize it, but it will be loss of your energy. So so this is called anisotropy of magnetic material or magnetic anisotropy. That means the magnetization is direction oriented, is direction towards a plane. Direction means direction towards a plane. It is direction oriented. Now next one is the hard and soft magnetic material. Hard and soft magnetic material. Sorry, material. Hard and soft magnetic material. Now, you see, we have given here two hysteresis loop. If the hysteresis loop is like that, the blue one inside, this is called soft magnetic material. Now, that means that low coercivity. The coercivity is very small. You see here, the coercivity is very small and comparatively high remanence. Comparatively high remanence. Here you see, coercivity is small, remanence is high, and the saturation comes very easily at a very low H value. Saturation comes at a very low H value here, and remanence is high, and coercivity is low. That is called soft magnets. Soft magnets. You can magnetize it very easily. That is called soft magnet, and this is hard magnet. The coercivity as well as the saturation point. For to get the saturation, you have to give larger H value. The remanence is high, but the coercivity is also high. This is called hard your magnetic material. Actually, if you want to get a magnet, if you want to magnetize magnetize a material permanently, then this should be a hard magnetic material. You have high saturation point and high remanence and high coercivity. And if you want a small magnet just working, small magnet just working, and then you can get a soft magnet. Soft magnet. You will get soft magnet in the small motors. You will find some small motors in some small particles. Say, for example, you have hair trimmer. You have hair trimmer here like that. There is a motor here. It is a small motor. Eh? There you will get the soft magnets. Soft magnets, and the permanent magnets are hard magnet. So what's the definition of hard magnet and what is the definition of soft magnet, and what will be their hysteresis loop will like will like rather. Huh? What will what will be their hysteresis loops? Huh? The fat hysteresis loop is for hard magnet, and a thin long hysteresis loop is for soft magnet, soft magnetic material. This is the data for several hard magnetic materials. You'll see tungsten steel. What is tungsten steel? You'll see 92.8% iron, 6% tungsten, 0.5% chromium, and 0.7% carbon. This is called tungsten steel. Its remanence is this, and coercivity is this, and its Curie temperature is 760. So these are some hard magnets. These are soft hard magnets. Q knife means copper, nickel, iron. This is called Q knife, copper, nickel, iron, copper. 20% nickel, 20% iron, 60% copper. That is called Q knife. It is also a hard magnet, sintered aluminum, nickel, cobalt. Nico, aluminum, nickel, cobalt. Sintered ferrite, cobalt rare earth. Cobalt rare earth means you mix rare earth element samarium with cobalt. So it is cobalt rare earth. It is also a hard magnet. Sintered molybdenum, iron, boron. Neodymium, iron, boron. This is also a very good hard magnet. Sintered neodymium, boron, iron is a very good hard magnet. So actually these are the magnets. These are the magnets we find in different instruments. These are the hard magnets we find in different instruments. We find magnets in different instruments. In NMR machine, you'll get magnet. In MRI, many of your relatives did the MRI, magnetic resonance induction. There is a magnet is there. They are generally hard magnet for big machine. Now, one more simple thing. This is actually theory of magnetic material. One more simple thing. We generally read with magnetic material. This is called superconductivity. That is called superconductivity. Now, what is superconductivity? Superconductivity means superconductivity superconductivity. What do you mean by superconductivity? It is actually an electrical phenomena. Superconductivity is actually an electrical phenomena, but we generally study it under magnetic properties because of a small region, rather. Now, what is superconductivity? If you say, for example, this is a curve for normal metal of electrical resistivity versus temperature. Temperature in Kelvin, rather. This is the temperature in Kelvin, and this is the electrical resistivity. Now, if you lower the temperature, the resistivity of electrical resistivity also decreases. If you lower the temperature, the resistivity decreases, and at 0 Kelvin, theoretically, the resistivity should be 0. But you will get some resistivity at 0 Kelvin for a metal. You will get normal resistivity, some resistivity at 0 Kelvin for normal metal. Why? Because of three things. One is that in metal there are some impurities. Second thing is that the metal crystal where you are in which you are doing the experiment, the metal crystal have some defects. Actually, due to this defect, you will get some resistivity. So a metal crystal is not always free from the impurities, or it is not always free from your defects. So you will get some resistance at 0 Kelvin also. But there are some metals where you will not get resistance after some point. Say, for example, mercury. When you come at 4 degree Kelvin, at 4 Kelvin for mercury, if you cool mercury up to 4 Kelvin, then you will see that there is no resistance. Mercury offers no resistance to the electrical conductivity. Naturally, our normal metals, say silver, say copper, say they offers resistance at 0 Kelvin. But mercury does not offer any resistance at 4 Kelvin. This phenomena is known as superconductivity. Some substance offers no resistance at some temperature. This phenomena is known as superconductivity. So in a superconducting material, you can pass electricity without any resistance offered by that material. Then you will get the maximum use of your current. You will get the maximum use of your current. This is known as superconductivity. And there are some substances which are superconductors. Now, why this superconductivity occurs? Why this superconductivity occurs for some substances? That is not very clear to the scientists still. But they are telling that the electrons the electrons which are responsible for the conductance of that material somehow coupled with other electrons. Somehow they coupled with other electrons, and they minimize the resistance offered by your impurities or your defects in that crystal. Somehow the electrons which are which are which are your what they call which are responsible for the resistance or conductance, they become somehow coupled. They become somehow coupled. So, so they minimize the resistance offered by the defects in the crystal, and as well as the resistance given by the impurities, and hence they become superconductor. So there are some superconductors you see here. Tungsten is a superconductor. Titanium is a superconductor at 0.4 K. Aluminum is a superconductor at 1.18 K. Tin is a superconductor at 3.72 K. This K is known as TC. That means the temperature below which a material becomes superconductor is known as TC. TC means the temperature below which a material becomes superconductor. So lead is superconductor at 7 Kelvin. But you will find the superconductor at high temperature for the compounds. You see, niobium titanium alloy is a superconductor at 10 K, and niobium germanium alloy is a superconductor at 23 K. But some ceramic compounds, you see, these are complex ceramic compounds. You will find that mercury, barium, calcium, copper, oxygen, this type of superconductor can show superconducting property at 153 K. This is very promising. This is very promising because we can supply current without losing any current in a superconductor. 153K, 153K, you can get 153K by liquid helium. By liquid helium, you can get this also, but the goal of the scientist is to make a superconductor at liquid nitrogen temperature, because liquid nitrogen is very cheap. So if you dip a superconductor, in a liquid nitrogen, if you place a material in liquid nitrogen, and if it becomes superconductor, then you can use a superconductor very cheaply. So then MRI machine will be very cheap. Our NMR machine will be very cheap. In the NMR machine, you require liquid helium and liquid nitrogen both to make the magnet superconductor. For that, we cannot actually afford an NMR machine. You can buy an NMR machine easily, but you cannot maintain it because the price of liquid helium is very high. So you cannot maintain it. So this is about the superconductor and magnetism. Now the next portion is the the magnetic materials, the use of magnetic materials actually. What is the use of this type of magnetic materials? Uh, the main use of magnetic material is in storage. Storage of what? Storage of data. The main use of magnetic material is storage of data. You are storing data in your hard disk drive. This is the main use of magnetic material. And there are other uses also of a magnet. As I told you, in NMR, in MRI, and in various places you'll get magnets. The modern use is the of magnetic material is to store a data, but not in your mobile phone or not in your pen drive. They are SSD type of storage. SSD type of storage. Say, for example, you have your mobile phone with 64 GB hard disk drive. These are not magnetic materials. These are SSD type of storage, and this is an electrical material actually, electrical material. But the hard disk drive of your laptop, say for example 1 terabyte, 2 terabyte hard disks you have in your laptops or in your desktop material, where the material is spinning. When you start your laptop or when you start your desktop material, something is rotating. This is the hard disk drive. This is the hard disk drive, and it stores say for example 1 terabyte data, 2 terabyte data, and much larger amount of data. This is the main use of magnetic material in modern life. You can find a hard disk drive very easily. 1 terabyte hard disk drive by about 5,000 taka. By 5,000 taka, or 2 terabyte, it is 8,000 taka. It is very cheap. But SSD drives are very costly. SSD drives are very costly, but magnetic drives are very cheap. Now, how a hard disk drive works? I can show you 3 videos, and you have to learn it from that video, because after seeing that video, you'll understand why I have shown you the videos, because it is not possible for me to draw it and to teach you. It is better to show you the video. ওকে, আমরা এখন ভিডিওটা একটু দেখি। আচ্ছা, ভিডিওটা দেখার আগে তোমরা আমাকে একটু বলো যে তোমাদের কোনো কোশ্চেন আছে কিনা। কারো কোনো কোশ্চেন আছে কিনা? আমি যা পড়িয়েছি এগুলো বুঝো নাই কিনা? কোনো কোশ্চেন আছে এই ইয়েতে? এনিবডি? সবাই বুঝেছো? তোমাদের শোনো, আজকে এটা শেষ হয়ে যাবে, কালকে কিন্তু পরীক্ষা নেব আমি। বুঝতে পেরেছ? পরীক্ষা যেহেতু মুখস্থ করতে হবে না, জিনিসটা বুঝলেই হবে, কাজের সমস্যা তো কিছু নেই, তাই না? কি বলো, ঠিক আছে? কালকে একটা 10 মার্কের ছোট ইয়েস নো টাইপের পরীক্ষা আর কি, হ্যাঁ, টিক দেবা। কাজে এটা তো কোনো সমস্যা কিছু নাই। হ্যাঁ, একটা চ্যাপ্টার শেষ হোক, একটা পরীক্ষা চলুক, অসুবিধা কি আছে? তাহলে পরীক্ষার সংখ্যা যদি বেশি হয় তাহলে সুবিধা হচ্ছে যে একটা খারাপ করলে তো আরেকটা ভালো হয়ে গেল, বাস এটা একটা মিনিমাইজ হয়ে যাবে আর কি, বুঝছো না? পরীক্ষা একটা বা দুইটা থাকলে খারাপ করলে তো করলেই শেষ।
স্যার আমরা পরের রবিবার দিই পরীক্ষাটা।
পরের রবিবার দিলে সুবিধা হবে?
জি স্যার, পরের রবিবার হলে ভালো হয়।
কি সুবিধাটা হবে বলো তো আমাকে?
বইটা স্যার পড়ি নাই স্যার এখনো।
জি স্যার, আপনার ক্লাসগুলো দেখছি কিন্তু বইটা পড়া হয় নাই।
এইটা কেন করো তোমরা বাবা, সেটা আমাকে বলো। এমন কোনো প্রেশার তো নাই যে তোমাদের যে ই হবে। আমি তোমাদেরকে এখন থেকে বলে দিচ্ছি যে যে চ্যাপ্টারটা শেষ হবে যেদিন, তারপরের দিন পরীক্ষা হয়ে যাবে। পরের রোববার দিতেই পারো, হ্যাঁ, দেখবো আমি কি অবস্থা। ঠিক আছে, ওকে, পরের রোববার দাও, দেখি তোমাদের কি হয় আর কি, বই পড়তে কতক্ষণ লাগে আর কি হয় আমি একটু দেখি পরের রোববার। হ্যাঁ, ঠিক আছে, পরের রোববার, আমার কোনো সমস্যা কিছু নেই। আমার কোনো সমস্যা কিছু নেই। তোমরা যেভাবে পরীক্ষা ভালো করো সেভাবে পরীক্ষা দিতে আমার কোনো সমস্যা নেই, খালি দেখে দেখে না দিলেই হলো। সেভাবে সবচাইতে ভালো করবা, কিন্তু সেটা না, অন্য যেভাবে ভালো করো অসুবিধা নেই কোনো। আচ্ছা, তাহলে আমরা এখন দেখব 3টা ভিডিও। একটা হার্ড ডিস্ক ড্রাইভ কিভাবে কাজ করে, হার্ড ডিস্ক ড্রাইভ অফ ইয়োর কম্পিউটার। এই ভিডিওগুলো একটু আস্তে আস্তে কথা বলেছে, এর জন্য সুবিধাও আছে। তোমাদের যা নোট করে নেবার এখান থেকে নোট করে নেবে, হ্যাঁ।
Welcome to HDS6 Incorporation.
তোমরা
Today,
দেখতে পাচ্ছ
I
তো?
am going to discuss about the structure of hard disk
শোনা যাচ্ছে?
drive, which is commonly abbreviated as HDD.
হ্যাঁ, আমাকে বলো,
Hard disk
শোনা
drives
যাচ্ছে নাকি
are
শোনা
the
যাচ্ছে না?
secondary storage.
শোনা যাচ্ছে কিন্তু কিছু দেখতেছি না।
দেখা যাচ্ছে না স্যার।
দেখা যাচ্ছে না, তাই না? সেটা বলো। আবার শেয়ার স্ক্রিন দেই। এবার
জি স্যার, দেখা
জি
যাচ্ছে।
স্যার।
Everyone,
শোনা
welcome
যাচ্ছে?
to DS6
Yes, sir.
Incorporation.
আচ্ছা, দেখো।
Today, I am going to discuss about the structure of hard disk drive, which is commonly abbreviated as HDD. Hard disk drives are the secondary storage device for any computer system and act as permanent storage for the computer system. Let's watch the next part of this video, and then I will explain in details.
The hard drive has been the main storage device in computers for decades now. Do you ever wonder what's on the inside? Hard drives are sealed so that no dust can get inside. Once you take yours apart, it most likely will not work anymore. The platters is where the information is stored. Both the top and the bottom of each platter is used so it can store as much information as possible. The actuator arm is how it reads and writes information. They never actually touch the platters, but you need a microscope to actually see that. It moves so fast that the human eye will have trouble keeping up with it. The platters are split up into tracks, and each track is split up into sectors. When you read or write to the hard drive, the actuator arm must find the right track, and the platters must rotate so the right sector is underneath the arm. It only takes a few milliseconds for this to happen. This may seem fast, but compared to newer technologies, this is much slower. In recent years, the hard drive is being replaced by the SSD, also known as the solid-state drive. These have no moving parts on the inside, which means they are faster, smaller, and use less power. However, SSDs are still a lot more expensive than hard drives. How long before the hard drive is obsolete? Only time will tell.
Now, let's see the structure of the hard disk drive in details. The traditional hard disk drive can have the following basic structures. A hard disk drive can have one or more platters. These platters are made of a non-magnetic rigid material, usually aluminum alloy, glass, or ceramic. And they are coated with a shallow layer of magnetic media material. Each platter has two working surfaces. These surfaces of the platters hold the recorded data. A typical HDD design consists of a spindle motor that holds flat circular platters. Spindle motor plays an important role in hard drive operation by turning the hard disk platters. A spindle motor must provide stable, reliable, and consistent turning power for many hours of continuous use. Many hard drive failures occur due to spindle motor not functioning properly. Each working surface of the platter is divided into a number of concentric rings, which are called tracks. The collection of all tracks that are the same distance from the edge of the platter is called a cylinder. The data on a hard drive platter is read by read-write heads of read-write arm. The read-write arm is also known as actuator. Each on a separate read-write arms are controlled by a common arm assembly, which moves all heads simultaneously from one cylinder to another. Now, let's see the structure of the platter in details. In order to maintain the organized storage and retrieval of data, the platters are organized into specific structures. These specific structures of platter includes tracks, sectors, and clusters. Therefore, let's give you the idea about the details of platter structure. So, now, let's see the structure of platter in details. Each platter is broken into thousands of tightly packed concentric circles, known as tracks. These tracks resemble the structure of annual rings of a tree. All the information stored on the hard disk is recorded in tracks. Starting from 0, at the outer side of the platter, the number of tracks goes on increasing to the inner side. Each track can hold a large amount of data, counting to thousands of bytes. Each track is further broken down into smaller units, called sectors. As sector is the basic unit of data storage on a hard disk, each track has the same number of sectors, which means that the sectors are packed much closer together on tracks near the center of the disk. A single track typically can have thousands of sectors. The data size of a sector is always a power of 2, and is almost always either 512 or 4096 bytes. Sectors are often grouped together to form clusters. A cluster is the smallest possible unit of storage on a hard disk. If contiguous clusters are not available, then the data is written elsewhere on the disk, and the file is considered to be fragmented. A spindle motor holds flat circular platters. The data on a hard drive platter is read by read-write heads of read-write arm, or actuator. With the help of spindle, platter starts rotating. And the actuators moves up and down to read or write the data from the desired sector of a cluster of a track. So, for this video, this is all about platter, track, cluster, and sector. Now, suppose I want to listen to music, what will happen with platter, track, cluster, and sector? Let's enjoy that part of animation with a music track.
ওকে, সেকেন্ড ভিডিওটা একটু দেখো। এটাতে কয়েকটা ডেফিনেশন পাবা, কয়েকটা নাম দেখা যাচ্ছে।
If you have missed the first structure of the hard disk drive in details, the rate at which data can be transferred from the disk to the computer is composed of several steps. Today, I am going to discuss about those. These are seek time, rotational latency, access time, read time, and transmission time. Let's watch the next part of this video to understand these concepts. Let's first discuss about seek time. The time required by the read-write head assembly to move or reach, or find, the desired track, or cylinder. That is, move to, one track, or cylinder, to another, is known as, seek time. Now, let's discuss in details. Okay. Can you remember this diagram from the previous discussed video, that is, hard disk drive structure part 1 video? This diagram contains major parts of any hard disk drive. For example, platter, track, cylinder, spindle, read-write head, etc. Now, if I remove all the parts except platter and track, then how will be the structure looks like? Yes, it will look like this diagram. That is a diagram with only platter and track. This is the side view of the platters and tracks. In this diagram, there are 3 platters. Platter 1, platter 2, and platter 3. And each of them having 2 tracks. If we want to see the top view of these 3 platters and tracks all together, then how it will be looks like. I repeat, if we want to see the top view of these 3 platters and tracks all together, then how it will be looks like. Sure, it will look like this diagram. I can visualize only one platter and its 2 tracks from the top view. The other 2 platters and their individual tracks are in exactly same position at bottom of the platter 1. I repeat, the other 2 platters and their individual tracks are in exactly same position at bottom of the platter 1. What I mean that the collection of all tracks that are the same distance from the edge of the platter or from the spindle of the platter can be connected to form a shape. I repeat, the collection of all tracks that are the same distance from the edge of the platter or from the spindle of the platter can be connected to form a shape. So, to get that shape, let's remove all the platters and keep only their tracks. Then, it will look like this diagram. Now, if I connect the all tracks that are the same distance, what will happen? Then, it will look like this diagram. So, basically, all connected tracks that are the same distance, forming a shape, which looks like a cylinder. I repeat, all connected tracks that are the same distance, forming a shape, which looks like a cylinder. Therefore, I guess you have understood the concept of cylinder. It is very important to understand cylinder to understand the concept of seek time. Therefore, the cylinder 1 is formed by track 1 of platter 1, then track 1 of platter 2, and track 1 of platter 3. And the cylinder 2 is formed by track 2 of platter 1, then track 2 of platter 2, and track 2 of platter 3. Now, let's add the read-write head and the actuator arm with this figure. And, as you already know, that, to read, or write data, from track, the whole read-write assembly, moves, all together. I repeat. To read, or write data, from track, the whole read-write assembly, moves all together. Now, suppose, the system, has to read a data, from, track 2, of platter 1. Then, the read-write assembly, will moves all together, towards, its desired track. And, even, you can visualize, that, it is moving towards, different cylinder, at the same time. But, the status, of the read-write arm 1, will be moving, and activated. Others, that is, the read-write arm 2, and, the read-write arm 3, status, will be, moving, but deactivated. Once again, suppose, the system, has to read a data, from, track 2, of platter 3. Then, the read-write assembly, will moves all together, towards, its desired track. And, even, you can visualize, that, it is moving towards, different cylinder, at the same time. But, the status, of the read-write arm 3, will be moving, and activated. Others, that is, the read-write arm 1, and, the read-write arm 2, status, will be, moving, but deactivated. So, can you visualize that, to move, or reach, or find, the desired track, to read the data, by the read-write assembly, it is taking some time, because it is, not in desire, or, proper, track, or, even desire cylinder. I repeat. Please, try to visualize that, to move, or reach, or find, the desired track, to read the data, by the read-write assembly, it is taking some time, because it is, not in desire, or, proper, track, or, even desire cylinder. Then, tell me, what is this time called? Yes. This time is called, seek time. So, the time, required by the, read-write head assembly, to move, or reach, or find, the desired track, or cylinder. That is, move to, one track, or cylinder, to another, is known as, seek time. So, I guess, you have understood, the meaning of, seek time. Next, rotational latency. Now, let's, discuss about, rotational latency. The time, required by the, read-write head assembly, to move, or reach, to the desired sector, of the desired track, is known as, rotational latency. Now, let's discuss in details. Okay. Can you, remember, this diagram, from the previous discussed video, that is, hard disk drive structure part 1 video? This diagram, contains, major parts, of any platter, of hard disk drive. For example, track, cluster, sector, etc. Now, from this diagram, let's take only one track to understand rotational latency. Here, I have taken only one track from a platter. If I make it little thicker and further broken into small equal size unit, that is sector, then the track will look like this diagram. As you already know that these small equal size unit are known as sector. Here, there are 8 sectors. These are Sector 1, Sector 2, Sector 3, Sector 4, Sector 5, Sector 6, Sector 7, and Sector 8. To read the data from the sector, let's add one read-write head assembly. Here, in this diagram, the read-write head assembly is in Sector 1. Suppose the desired data is in Sector 5. I repeat. Here, in this diagram, the read-write head assembly is in Sector 1. Suppose the desired data is in Sector 5. So, the platter will rotate, hence, the sector will rotate too, to reach the desired sector, by the read-write head assembly. I repeat. The platter will rotate, hence, the sector will rotate too, to reach the desired sector, by the read-write head assembly. Let's watch that, how a read-write head assembly is reaching the desired sector. Can you visualize that, to move, or reach, the desired sector, that is, Sector 5 here, to read the data, by the read-write assembly, it is taking some time, because it is not in desired, or proper sector. I repeat. Please try to visualize that, to move, or reach, the desired sector, that is, Sector 5 here, to read the data, by the read-write assembly, it is taking some time, because it is not in desired, or proper sector. Then, tell me, what is this time called? Yes. This time is called rotational latency. That is, a delay, or latency time, due to rotation. I repeat, that is, a delay, or latency time, due to rotation. Therefore, the time required by the read-write head assembly to move, or reach, to the desired sector of the desired track is known as rotational latency. So, I guess you have understood the meaning of rotational latency. Next, access time. Now, let's discuss about access time. Access time is nothing but the summation of seek time and rotational latency. I repeat, access time is nothing but the summation of seek time and rotational latency. That is, the time taken by the read-write assembly to reach desired track plus the time taken by the read-write assembly to reach desired sector. Therefore, I guess you have understood the meaning of access time. Next, read time. Okay. Now, let's discuss about read time. The time required by the read-write head assembly to read the whole desired sector is known as read time. Now, let's discuss in details. Suppose the read-write head assembly has reached its desired track, and then its desired sector. Then, what will be the next task? Yes. Next task will be reading the whole desired sector, where the read-write head assembly has just reached. Let's assume, here it is the sector 1. What does a sector contain? It contains a head, which contains sector identifier. Then, a body, which contains the actual data. And, finally, a tail, which contains error checker, to check whether recorded data is correct or not. Let's watch the movement of the read-write head assembly. Can you realize it is taking some time to read the whole sector? What does this time called? Yes, this time is called read time. Therefore, the time required by the read-write head assembly to read the whole desired sector is known as read time. So, I guess you have understood the meaning of read time. Next, transmission time. Transmission time is nothing but the summation of access time and read time. I repeat, transmission time is nothing but the summation of access time and read time. Therefore, I guess you have understood the meaning of transmission time. Okay. That's all for part 2.
লাস্ট পার্ট, এটাই হচ্ছে আসল, কিভাবে লেখা হয়।
Welcome to. Today, I am going to discuss about reading and writing process of the hard disk drive. This is the last part of the discussion about structure of hard disk drive. If you have missed the first and second part of this below, let's watch the next part of this video to understand reading and writing process of the hard disk drive in details. An object can be magnetized with the north or south pole, or either end. You may already know that the data stored in computer as a series of ones and zeros, which is a machine language commonly known as binary code. But how can we represent a 1 and a 0 magnetically? So, let's check the next part. A bit is the smallest unit of data storage. It can be visualized as a many-scale blocks that can be magnetized into a permanent magnet. Every red, blue, or gray block in this picture is a bit. The red blocks have north poles facing up, and the blue blocks have north poles facing down. These are with the computer recognizes as 1 and 0. Gray blocks are the empty bits that are not yet been magnetized. The read-write head assembly has 2 separate heads. The red head and the write head. The write head is basically an electromagnet with a coil property shaped like this. To direct the magnetic field into a bit, it magnetizes it as it passes by. It can magnetize a bit, as a north facing up, or a north facing down, simply by changing the direction of the current in the coil. As you may remember, reserving the direction of current in an electromagnet results a reverse in the direction of the magnetic field. Now, let's check the writing process by the write head of the read-write head assembly. Please try to visualize that the direction of the magnetic field and the direction of the current against the writing ones and zeros. Therefore, I guess, you have understood the process of writing by the write head. Next, reading process. Once written, the bits can be read by the read head, which senses the direction of the magnetic field as it goes over the written bit. Now, let's check the reading process by the read head of the read-write head assembly. Therefore, I guess, you have understood the process of reading by the read head. A hard drive, as a whole, looks like this. Both the read head and write head are the tip of the actuator arm. The motor of the disk and the motor of the actuator arm collaborate to align a desire bit with the read head or the write head at any given time to read it or write it. The hard drive keeps the data, even the power is turned off.
বোঝা গেছে?